introduction to limits, and you're going to learn how to use them and why we use them. So starting with example 1 in your book on page 806, look at that, and here it is, Introduction to Limits. Okay. And we'll do examples, so you might not understand what it is while we're doing the first couple examples, but as we go through, okay, you'll understand better the further we get, the more examples we do. So just be patient, okay? So example 1, you're given 24 inches of wire. You are given 24 inches of wire and are asked to form a rectangle whose area is as large as possible. What dimensions should the rectangle have? All right. So if they tell us we have this piece of wire, it's 24 inches long, what are they telling us about the rectangle? The perimeter, right? So let's write example 1. We have our perimeter of our rectangle is 24 inches. And let's draw our rectangle. Generally, a rectangle has a width and it has a length. And so how do we find the perimeter of a rectangle? What do we do? Okay, so it has 2 widths plus 2 lengths, right? So we have a width here, a length there, and a length there. So we add those 4 sides together. 2w plus 2l equals the perimeter. But they told us the perimeter is 24, so we can substitute 24 into there. 24 equals 2w plus 2l. All right. Now, they also told us we want to maximize the area. So we want to find the area of this rectangle and we want to maximize it, because there's lots of different rectangles we can make, right? We can make a long skinny rectangle, we can make a square, we can make just, a rectangle like this. There's so many different rectangles and they can all add up to 24 different ways that we could bend the wire. So we want to find what's going to give us our maximum area here. Okay, so let's make an equation for area of our rectangle. We'll put area over here. How do you find the area of a rectangle? Length times width, right? Base times height. In this case, length times width will give us the area of the rectangle. Okay, so we have too many variables going on here, so let's solve for L and substitute in for L there. So let's solve this equation for L and substitute it into here so that we get rid of the L. Okay, so one thing I'm going to do, since these both have a 2 in them, I'm going to take a 2 out and put W plus L. 2 times W plus L equals 24. Oops, equals 24. And then just divide by 2 to get rid of that 2. Divide by 2. 24 divided by 2 gives me 12 equals W plus L. And then subtract W from both sides. That. And you get 12 minus W equals L. So now that we solved for L, I'm going to plug this 12 minus W in to my L right here. So my equation is the area equals 12 minus W times W. And so basically we have a function here. Our function is in terms of W, but usually we have a Y and we have an X. So let's go ahead and multiply this out, distribute it to simplify it, and we get area equals 12W minus W squared. Like I said, this is just a function. Normally we have a function like f of x is equal to, this is just 12x minus x squared. So we want to maximize this area and find what value of W do we put in here to get our maximum area. Okay, to do that we can use limits, and we can actually we can graph this and put this in our graphing calculator. So if I were to put this in my graphing calculator, what kind of graph would I get for 12x minus x squared? You get a parabola, right? It's an x squared, and there's a negative in front of the x squared, so what kind of parabola would you get? It's going down, right? It's somewhere on the xy axis going down. So to find what it looks like, let's put it in our graphing calculator. So get your graphing calculators. Since we're doing polar coordinates, let's get out of polar coordinates. Okay, so let's go to mode, press the mode button, and if you're still in polar coordinates, which you probably are, polar's over there, So change it back to function mode. Let's get out of radians because we're going back to just regular numbers, so degrees. Okay, so change out of radians, go to degrees, go to function, get out of polar, and then we have to change our zoom factor, so our format. So press second zoom to change, because a lot of you are still in polar mode, so we need to get over to rectangular mode. And you pressed a second zoom there. Okay. Once we do that, then we can go back and put in our equation here. Our equation is 12x squared, 12x squared minus x. I'm sorry, just 12x minus x squared. Got those backwards. So 12x, delete that squared. 12x minus x squared. Okay, that was our equation. When I try to graph this, let's see if I get my, okay, I don't get a parabola, and a lot of people have said, oh, they got a line. Okay, I kind of got a line. Well, this is the left-hand side of the parabola. The parabola actually goes over here. So I need to move my window to the right. So I don't need negatives, so I'm going to make my x go to the positives, and I'm going to make my y values go higher so I can see the... So you have to go to your window. You always have to fix your window when you're doing these problems. And my window is really small right now. So I'm going to change it to 0 for my x's, and I can change it to 10 for my maximum x. My y values, my minimum 0, and let's say, I think for this one we have to go really high up. I'm going to go to 50 because we tried 10, we tried 20, the last class period, it was too low. So I'm going to go all the way up to 50. Okay, and then press graph. Alright, got a pretty good graph. All I really care about is the maximum. You know, I could make my window, my x go a little further. Why don't I do that? Why don't I go to 20 instead of 10? And then change, so it'll change my window a little better. So now I can see like the whole left and right side of the parabola. Of course, it goes on forever. So I want to find where the maximum is. So I'm going to press trace. Okay, so trace is this button right here, and then it'll pop up somewhere. I want to move it to the left and watch my values of y. Look what they're going to, because this is what we're interested in. This is going to be our area, and we want to see what the area is going to go up to, and we want to find what x value is going to give me my area, because that x value is the width of the rectangle. Right? So it's getting higher, 26, 20, 20, 28, 29, 30, 32, 33, 35. What is it going to go to? Close to, what do you think the top was supposed to be? 36, right? So x equals 6, 36. If we're not sure, let's type in a 6. So I'm going to type in, I'm going to press 6, and it's going to say x equals 6, and then I press enter, and it'll tell me what coordinate goes with 6. So at 6, the y is 36. So that's going to be our maximum. Okay, that's going to be the maximum area of 36 square units for a 6-inch width rectangle. Okay, so the way that we write that, we just found a limit. We found the limit, LIM, as x approaches 6, because that's where, you know, the highest point was, of our function 12w, or I should put x. I'll put 12x minus x squared, because this is an x. Our limit is 36, and that's your first example of finding a limit. So this point up here was 636. Okay, when we got to 6, the graph approached 6 from the left and from the right. So that's a real life example of how you could use this limits. Okay. Oh, definition of a limit. So next I want you to copy down this definition of a limit right here. Okay. This is the definition. You won't really understand it, but that's okay. Just copy it down. You'll understand it soon. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L. This is written as the limit as x approaches c of f of x equals L. Okay, so go ahead and copy that. I'll pause it for a second. Example 2 here. Let's do another example. So we're going to use a table to estimate numerically the limit of 3x minus 2 as x approaches 2. Okay, so let's write that out first. Example 2 says use a table. Use a table to estimate the limit the limit as x approaches 2. So they can change this number to whatever number they want, and we're going to 2 as of 3x minus 2. Okay, so this is just the function y equals 3x minus 2. Well, what kind of graph is that? It's just a line, right? So we don't need to put that in our graphing calculator. We can graph that by hand. So -1, -2, 1, 2, 3, 4, 5, 1, 2, 3, 4, right here. So I'm going to start at -2, which is down here. And then I'm going to go up 3 over 1 for my slope. So 1, 2, 3 over 1, 1, 2, 3 over 1, do it a couple times. And then I'm going to make my graph, my straight edge right here. Okay. The point that we really care about is where x equals 2. We want to look at what's going on at x equals 2. Okay, so what's the y coordinate when x equals 2? 4, right? 2, 4. If we're not sure, let's plug it in. So let's actually plug in 2 into here, since we want to find out what is happening at x equals 2. So 3 times 2 minus 2 is 6 minus 2, so that equals 4. Okay, so we do have the point 2, 4. Okay, what is the limit at 2, 4? It's 4, because when we plug in 2, we get 4. But what's the purpose of limits if we just plug them in? Well, sometimes it doesn't work that way. What we want to look at is what's happening to the line when we come in from the left side of the point and we come in from the right side of the point. Is it approaching the same number? 4. Yes, it is. Okay. We want to look at our table too, our table values. So if we were to put this in our calculator, we would get a bunch of numbers like this, right? And we would get 2, 4. But what we want to look at is what's happening to the left of 2 at 1.99, at 1.99, at 1.9? Is it approaching 4? Are the numbers getting bigger and bigger close to 4? Yeah. How about after 2 at 2.001, 2.01, 2.1? Are the numbers close to 4? Yeah, they're getting bigger than 4. So if these numbers are both approaching 4, then our limit is whatever number we plug in when we get 2. When we plug in 2 is 4. So that is our limit. Our limit is 4. Okay? So, yeah, that's easy enough. The limit is 4. So this limit is 4. So you just plug it in. Okay, the problem comes when you plug in a number and you don't get the limit. Okay, like example 3 here. So if we look at example 3, I think I have enough room here. Example 3, it says use a table to estimate numerically the limit, find the limit as x approaches 0 of x over the square root of x plus 1 minus 1. Okay, now let's plug in 0 into this function and see what we get. So when I plug in 0, I get 0 over the square root of 0 plus 1, which is 1, minus 1. So I get basically 0 over 0. Okay, what is that equal to? What's 0 over 0? It's undefined, and that's what he said in the video yesterday. It's not 0, it's not 1. Somebody said 0 in the video, and he like freaked out. No, it's not. 0 over 0 is not 0, it's not 1, it's undefined. Okay, so if it's undefined, that means there's some kind of gap in the graph at when x is 0, there's going to be a hole, or there's going to be an asymptote, or something funky is going on there. So what can we do to find the limit? We have to look at what's happening to the left of 0 and what's happening to the right of 0. And to do that, we're going to put that in our graphing calculator and look at the graph. Okay. So generally, what do square root graphs look like? Square roots of x, they look like a sleeping parabola, half of a sleeping parabola, right? So let's see if this one looks like that. Let's go to our y equals, plug in our equation. Our equation is x divided by, and then you got to put parentheses. Another big thing about this is you have to put parentheses in the correct place. We're going to have to put parentheses around this whole bottom denominator, or else you're going to not do it correctly. It's not going to graph the correct problem. Okay, so parentheses square root of x plus 1 and your square root, and then minus 1, and then another n to your square root, right? So I put x divided by this square root minus 1, so this is my whole denominator right there. Okay. And now I'm going to look at my window. Let me look at my window. Yes, I think I do want to go from 0. Actually, we want to go around -1. Let me put -2 in there. And my x minimum, I think I only need to go to 10. So, and the 50 I think is too high. Let me change that to 20. And I think we'll be good if we do that. And let's graph this guy. Alright, so yeah, I do get like a sleeping parabola, but I've got a big empty space over here, so let me bring that window down a little bit. So I'm going to go to, instead of all the way up to 20, I could probably go to 5 or something, or 6. And then make it nicer. So that's a better graph, right? It's much better. Okay, but what we care about is when x is approaching 0. Okay, so we're going to look at the graph when we have our xy graph. What's happening when we get closer and closer to 0? What's happening to the left of 0 and to the right of 0? Okay, so to do that, we're going to look at our table, or we can do our trace too. We can do our trace. I can go all the way to 0. But I can't quite get there, or it looks like it's going to be around 0, 2, right? So I keep going. Is it around 2? Yeah, the numbers are getting closer and closer to 2. And, when I plugged it in, I didn't get a 2. I got 0 over 0, which told me nothing. But if I go to my table, I do second graph. Let's look at my table. Oh, I have weird table sets. So another thing you need to be able to do is second window and change your table set. I'm going to change my table set to like 0.1 instead of 0.06, and -0.3. If I start at -0.3, that's fine. So table set, and so I can see, 1.8, 1.8, 1.9 error. Error is my 0 over 0, and then 2.04, 2.09. So it should be a 2. If this continued in a logical manner, it would be 2, right? So that's why this limit, as it approaches x, is 2. As x approaches 0, is 2. Okay? And so, we get an error here, but we get like 2.04 here. We get 2.09. We get 2.14. On the left of 0, we get 1.94. And then we get 1.89, and then we get 1.83. We can see that from the left side of the graph, it's approaching 2, and then it's also approaching 2 from the right side of the graph. Now, I do want you to draw the graphs as well. So our graph started at -1, 1 right here, and then it went up to 0, 2. And there's a hole, though. There's a hole in the graph at 0, 2, so you need to put like an empty spot there. That hole doesn't appear in your graphing calculator. I don't know why your graphing calculator is not capable of putting a hole in it, but it's supposed to have a gap there, right? So there's no value at 0, right? If we do f of 0, it's undefined. But it does still have a limit. The limit is still 2, because the graph is approaching 2 from the left, and the graph is approaching 2 from the right. So it does still have a limit, even though the value at 0 is undefined. Does that make sense? Okay, that's the big thing. You can still have a limit even though there's no undefined value at 0. Okay, so let's look at another example. Let's flip to the next page, example 4. It says to switch pens, you can still see this. Example 4 says to use a graphing utility to find the limit. We want to estimate the limit of as x approaches 1 of x cubed minus x squared plus x minus 1 all over x minus 1. So what do we do first is see if we can just plug it in and find our limit. So we're going to plug in 1 into all these x's and see what we get. Okay, we're going to get 1 cubed minus 1 squared plus 1 minus 1 all over 1 minus 1. I already see a problem in the denominator because when I get 1 minus 1, we're going to get 0 in the denominator, which means already it's going to be undefined. And then when we do this, we get 1 minus 1, which is 0, plus another 1 minus 1, which is another 0. So again, we get 0 over 0, which is undefined. So the value when x equals 1 of y is this becomes undefined. But there's stuff going on. Does it mean that there's not a graph? No, there's still a graph, right? So we can look at what's happening to the left of 1 and to the right of 1 to find the limit. So that's what we're going to do. So we're going to look at the table, and we want to go to 1, and we want to see what's happening. What's happening around 1? What's happening at like 1.1, at 1.2, at 1.3? What's happening at 0.9, at 0.8, at 0.7? Okay, we know we're going to get an error here, but hopefully they're going to be numbers that it's approaching a number. We can tell what that limit is. Okay. So to do this, again, we plug this function into our calculator. Again, you're going to have to put parentheses around the top and the bottom to, hold all that together. So I'm going to clear out my last function. I'm going to put x cubed, parentheses, forgot about the parentheses, x to the third power minus x to the second power plus x minus 1 parentheses divided by parentheses x minus 1 parentheses. Okay, so your numerator needs to be in parentheses divided by your whole denominator in parentheses. And let's see what this graph is. Let's see if we get a good graph here. If we might need to change our window. It's just a parabola, right? It's just a parabola. And we want to find out what's happening at 1. So we don't really care about the minimum here. We actually want to go, so I'm going to press trace and move it over to, oh, it's way over at 5 for some reason. So let me just type in 1. And it gives me undefined, right? So, there we go. So I'm getting closer to 1, and it looks like it's getting close to 2. So I go in 1, it goes right over 2. So yeah, it's approaching 2 as I get closer and closer to 1. So these values are like, let me go to my table setting, and you can see I want to go down to 1. Okay, so this is where I want to be. Here's my error, 1.4, 1.6, 1.8, so, 1.4, 1.6, 1.8, and then after 1 we get 2.21, 2.44, and 2.69. So you can tell that in between here is 2, right? So it should be the 0.12. So the graph looked like this, and at 1, 2 though, at 1, 2 there's a hole, so I should have put a hole there. But the rest of the graph is just a regular parabola. And from the left it's approaching 2, and from the right it's approaching the same number 2. So this limit as x approaches 1 is still of f of x, of our f of x, is still 2. Okay. Even though the value of 1 is undefined, the limit is 2. Because it's approaching 2 from the left, it's approaching 2 from the right, it's 2. Okay. So that's how you find a limit. Okay. That's nice when these are nice functions. They're easy functions because they're all continuous, even though sometimes they have a gap. But sometimes they're piecewise functions. So we're going to look at example 5, a piecewise function. It says find the limit of f of x as x approaches 3. As x approaches 3. And this is our function f of x. F of x is equal to 2 things, not just one thing. It's equal to 2 when x is not equal to 3, and it's equal to 0 when x is equal to 3. This reminds me about like a coding that you could do, because you could code things and you could say if the user answers yes, make it equal to. If the user answers no, then make it equal to 0. Alright, so what does this mean? It means our function is y equals 2, right? F of x is just another way of saying y equals 2 when x is not equal to 3. When x is equal to 3, then the function is equal to 0. Okay. So when x is not equal to 3 and when x is equal to 3. Well, y equals 2, that's just a straight line, right? That's just a line, let's say 2 is right here and 1 is right here. And the only time it's not equal to is when x is 3. So I'm going to go 1, 2, 3, and I'm going to put a hole at 3, 2, and the rest of the time it is equal to 2. And it is equal to 2 like that. Okay. So left side, right side. What is it equal to when it is equal to 3? It does have a value. It's equal to 0. So 3, 0 is the point. So we're going to fill in 3, 0. So to the left of 3, it's always equal to 2, equal to 2, equal to 2, equal to 2. Drop down, equal to 0, back equal to 2, back equal to 2, back equal to 2. So it's mostly always equal to 2, except for one time. When is that one time? When x is equal to 3. Anytime x is equal to anything else, it's equal to 2. Okay. So the question is, what's the limit? Is the limit going to be 2 or is it going to be 0? Okay, so the limit does not depend on necessarily the value of the function. It depends on what's happening to the left of the function and what's happening to the right of the function. So since the left is approaching 2 and the right is approaching the 2, the limit is actually equal to 2. So the limit as x approaches 3 of our function f of x is actually 2, not 0. Okay. So because we know f of 3 is equal to 0, but that's not the limit. Okay, that's the value of the function. So this is a case where the value of the function is different from our limit. Okay. Because again, we care about what's going on the left, it's at 2, and what's going on the right, it's at 2. If you looked at your table, right, it would just be a bunch of 2's, and there would be an error here in the middle. Like this would say 2, 2, 2, 2, error, 2, 2, 2, 2. So since these are all 2's, your limit is going to be 2. Alright, is there a time that the limit does not exist? Yes, there is. So a limit can fail to exist. So put limits that fail to exist. Example 6 says, show that the following limit does not exist. Show that the limit as x approaches 0 of the absolute value of x over x does not exist. Okay, first thing we should do is find the value of the function by plugging in 0, right? So we're going to plug in absolute value of 0 over 0. Well, the absolute value of 0 is 0 over 0. So again, we get undefined. That doesn't help us. So if we don't know what the value is at our function, we're going to look at what's happening to the left of the function and the right of the function by our graphing calculator. So your whole lesson, all your homework, you're going to do it on your graphing calculator today. Okay? So y equals absolute value. Uh-oh. How do we put absolute value in our calculator? Math button, right? Yep. Go to your math button. And it's not in the first menu, but if we arrow over to number, it's the very first option right there. ABS stands for absolute value. So absolute value of x, enter parentheses, divided by x. Okay. Usually an absolute value is like a, what kind of graph? A V, right? This one's not going to be a V though, because we're dividing by another x and that's going to change it. So let's press graph. And it looks like it's just a line, but actually there's more going on down here. So I want to move my window down into the negative section and to the left. So my window, I'm going to change to, let's make it negative 10. And then I need my Y, oops, I used the minus button. If you use the minus button, it'll give you an error. And then my Y value, my minimum, let's make it negative 10 as well. And then graph it. I get a line, and so I get two lines, two piecewise functions, and I get an open circle here and here. So, sorry. Okay, so this is what we get. We get at -1, we get a line, but then we get an open circle here. And then at +1, we have another open circle going to the right. Okay, because we know at 0, it's undefined both times. Okay, well, you know, so if we had our XY, our XY table, you know, and I put 0 in the middle, put 0 in the middle, and like, oh, -1, -2, -3 here, +1, +2, +3 there. These would just be -1s, -1, -1, coming from the left. The value is -1. After I pass 0, I get an error at 0. And then once I pass 0, I get a bunch of 1s. So what's the limit? Is it -1 or is it +1? It's neither. Okay, so if your graph does two different things. From the left, it approaches one number, but then from the right, it approaches a different number, then this limit does not exist. So limit does not exist. Okay, you can't do that. You can't approach from the left a different one and the right a different one, then it has no limit. Okay, and that's a good example of that. All right, example 7. A couple more examples. We're almost done. Let's look at example 7 here. Example 7 says, discuss the existence of the limit. Discuss the existence of the limit. The limit as the limit x approaches 0 of 1 over x squared. So first thing we do, right, we try and plug in 0 and see if we get a value. So 1 over 0 squared. Well, 1 over 0 squared, that's undefined because you can't divide by 0. So again, we have to look at the graph, we have to look at the XY table, we have to look at what's happening around 0. What's happening at like at a -1, at -2, at -3, so on at 1, 2, 3. Okay, so let's put this in our graphing calculator. And let's do 1 divided by x squared, which is pretty easy to enter, no tricks there. And then graph it. Ooh. Okay, so what I'm getting is a graph up there and a graph up there. Let me change my window. Let me get rid of the negatives because obviously we don't need any negative y's. So y, I'm going to get to 0 and then graph. It's a little nicer. Let's zoom in a little bit. So what's happening at 0 from the left is you have an asymptote there, right? It's never going to cross 0 because we got undefined. When we plugged in 0, we got undefined. So there's actually an asymptote, and it goes up to infinity, and it goes to the right to infinity. So is there a point where those are going to meet? No. So since it goes on forever and it's unbounded, we said there's no limit there. That limit does not exist, okay? So let's just sketch our graph and show, oh, towards 0, it went up to infinity. Towards 0 from the other side, it also went to infinity. So this limit does not exist. Okay, it can't do that. It has to meet somewhere to have a limit. It could have a hole in it, but it can't just take off forever. So, and example 8 is an example of oscillating behavior. Oscillating behavior. That's when behavior goes back and forth, like your best friend, right? You go back and forth, back and forth. One moment you're friends, another moment you're not, then you're friends, and then you're not. As x approaches 0, the sine of 1 over x. Okay, oscillating behavior. So we've introduced a sign in this function, okay? When we do sine of 1 over 0, you know, I plug in 0 into here, I get sine of 1 over 0. I can't evaluate that because that's undefined. So I have to look at the function, what's happening around 0. So let's enter this in our calculator. Okay, and I'm going to put sine of 1 over x. So sine of 1 divided by x. Okay, and then if I try to graph this, it's not really going to do anything unless I change it to radian mode. Okay, so let's go to, and then I need to change, I think, my window a little bit. Yeah, I need some negatives in here. So let me go back and put some, I'll go to -6 instead of that. And then I'll go to mode, and since there's a sine in, I definitely need to be in radian mode. And hopefully this will graph, because this is kind of hard to graph. Okay, did you see that? It was like a heartbeat. It went boop, boop, boop. But really, let's zoom in a little bit. Let's use our zoom in at 2 right there. And then the cursor is going to blink in the middle, and that's where I want it to zoom into, so I'm going to press enter. So that's really what the graph is, and maybe we could even zoom in more. So the graph is going up and down, it's bouncing up and down, and it's kind of irregular too. So this oscillating behavior, and then your book shows you like the values of, if you put your different x values in, what do we get? We get like +1, -1, +1, -1, +1, -1. So it's going up, down, and it's doing this thing really fast. Well, when you have oscillating behavior, there's no limit, okay, because it's just too irregular. So if that happens, no limit doesn't exist. Okay, so the limit does not exist here. And we could draw like a little graph of what it looked like. It went like down like this, then it went boop, 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 and then it went back like that. So because it's oscillating, limit does not exist. We use does not exist so much that we make an abbreviation for it. It's DNE. DNE. So if you want to write DNE on your homework, you can. We know that means it does not exist. Okay. And then the last part of the homework is just the properties. So take a look at those properties right there. I'm not going to, oh, I forgot to go over this. There are 3 times when limits do not exist. When f of x approaches a different number from the right side than from the left side. So, you know, if one part of the graph is coming down here, another part's coming up here, there's no limit. If it increases without bound as x approaches c, so if it takes off to infinity as it approaches c, then that's no limit. And then if it's oscillating, that's no limit. So those are the 3 cases when you have no limit, they do not exist. Okay. And then there's properties of limits. So your properties of limits, the limit as x approaches c of b is always going to be b, whatever b is. If that's 5, it's going to be 5. Okay. The limit as x approaches c of x, if you just have x, that's just a line. So whatever value you put in, if c is 5, then this x is going to be 5. If it's 8, then it's going to be 8. Okay. And then the limit as x approaches c of x to the nth is going to be c to the nth. So if this is, let's say 5, and you have x, let's say we have x to the 5th power, then it's going to be 5 to the 5th power will be your answer. And the limit as x approaches c of the nth root of x is going to be the nth root of c. So if this is as x approaches 5 of the square root, then it'll be the square root of 5 is your answer. Okay, which is pretty self-explanatory. The bottom part here, which I'm going to have trouble showing you, is if you have a scalar multiple, let's say you have like 5 times the function, and then you want to find the limit of that, well, you can just take, if f of x is, the limit of f of x is L, you can just take that scalar b, whatever scalar multiple you have, and multiply it by the limit of f of x. If you want to add 2 limits together, so let's say 2 functions together and then take their limit, well, let's call the limit of g of x k, right? Then you can just take the limit of this one and the limit of that one and add them together and do L plus k. If you want to multiply 2 functions and then take the limit, well, you could take the limit of f of x, L, and the limit of g of x, k, and multiply them. If you want to divide 2 functions and take the limit, you can just take the limit of f of x, L, and divide it by the limit of g of x, k. Okay, and then if you have f of x to the n and you want to take the limit of that, you could just take the limit of f of x, which is L, and raise it to the nth power. So these are just little properties that you can use for number 49 here. when you get to 49, you will use those properties. It's very easy. You can check the answers in the back end. You'll see, oh, that's really easy to do. You just add them together. So, yeah, so you're going to do that. All right, I was going to do number 1 with you, and then we'll be done, okay?